accounting, an energy balance for closed systems. So this is when we bring everything in this chapter together and we start using it to actually solve problems, which is kind of fun. So the first law of thermodynamics is a fundamental concept that energy is conserved. We have seen that the only ways that energy of a closed system can change are through transfer of energy by work or heat. So again, first law, the fundamental concepts of energy, the concept is that energy is conserved, and we have seen that the only ways energy of a closed system can be changed are through heat transfer of energy by work or by heat. So W or Q. So summarizing energy concepts, this is on page 61 and book animation A8. All energy aspects introduced to this point in the book can be summarized with these words. So the change in the amount of energy contained within a system during some time interval, so that is delta E equal E2 minus E1. That's what that side is the amount of energy transferred across the system's boundary by heat transfer during the time interval, that's Q, minus the net amount of energy transferred out across the system boundary by work during that time interval, so that's W. So here we have the energy balance is given by delta E equals Q minus W. So you remember we already had delta E, right? Delta E equaling the change in kinetic energy plus the change in potential energy plus the change in internal energy. So now we have our final, our energy balance equation where we combine these two equations and we end up with delta E equals delta KE, the change in potential energy, let me start again. The change in energy equals the change in kinetic energy plus the change in potential energy plus the change in internal energy, and that in turn equals the energy transferred by heat minus the energy transferred by work. And this is our energy balance equation and where we start our problems from. And if we start from here and we cancel out what we don't know and always go back to this, then we have the best understanding of what's happening and the best understanding of the equations. So note that Q and W have opposite signs. The minus before the W is because energy transfer by work from the system to the surroundings is taken as positive, and the plus sign before the Q is because heat transfer of energy into the system from the surroundings is considered positive. So we'll have some experience with that and get to use that and understand that a little better. All right, talking about a thermodynamic cycle. So we have our energy balance equation, and that will hold true in the things we're doing. But then we also have our energy analysis of cycles. So thermodynamic cycle is a sequence of processes that begin and end at the same state. So we go from 1 to 2, 2 to 3, 3 to 4, and then 4 to 1, if it's a 4-process cycle. It just always goes back to the beginning. At the conclusion of the sequence of cycles, all properties have the same values they had at the beginning. So they have the same values as they did at the beginning. So we know wherever we end up, we have to be going back to the values that we started at. And so with that, we can solve some thermodynamic cycle problems. Cycle energy balance. So the energy balance for any system undergoing a thermodynamic cycle takes the form of the change in energy of the cycle equals the change in energy of heat transferred by of energy transferred by heat minus the energy transferred by work. And so this is the energy balance for any system undergoing a thermodynamic cycle. So we know that if you sum everything up over that cycle, then that is true. Where Q cycle and W cycle represent the net amount of energy transfers by heat and work, respectively, for the cycle. Since the system is returned to its initial state after the cycle, there's no net change in energy. Therefore, the change in energy for the cycle has to equal 0. And the equation then reduces to, right, if we set this equal to 0, then we get Q cycle equals. This is true only if this is a thermodynamic cycle. So if it's a thermodynamic cycle, then this is true. And again, that reduces to this equation. Power cycles. So a power cycles are systems undergoing cycles that deliver a net work transfer of energy to their surroundings during each cycle. So essentially we're generating power and we're sending power out into the surroundings. A power plant, if you will, would be something like this. It's generating power and it's producing the power and it's sending it out into the surroundings. So you can see figure 217 on page 73, and that will help with this. So the energy transfer due to work of a cycle is heat transfer in minus heat transfer out. So again, we have our sign conventions, and we have to look at that. But if the Q in into the system, so Q in is greater than 0, and Q out is less than 0. Back to our sign convention. So if we're looking at a cycle, a thermodynamic cycle, and we have positive Qs, well, then that would be heat transfer into the system. And if we have a negative Q, then that would be heat out of the system. And overall, anyway, where Q in represents the heat transfer of the energy into the system from a hot body, and Q out represents heat transfer out of the system to a cold body. We do a lot more with this later, but this will come back around again. So for a power cycle, Q in has to be greater than Q out. So the amount of positive Qs is greater than the amount of negative Qs. And we'll do some examples, and that will make more sense. The performance of a system undergoing a power cycle can be described in terms of extent to which the energy added by heat, Q in, is converted to net work output in W cycle. So the conversion is expressed in the ratio called thermal efficiency. So only if we have a power cycle do we have thermal efficiency. And this Greek letter is eta. Eta. It's looks like an N, but it's eta. And it's the W of the cycle over Q in. And that's for a power cycle. If we have refrigeration or heat pump cycles, refrigeration and heat pump cycles, again, look at the animations. For cycles of this type, Q in is the energy transferred into the system from the cold body, and Q out is energy discharged by heat transfer from the hot body. To do this requires a net work input, so we have to put something into the cycle. And so for refrigeration and heat pump cycle, Q out is greater than Q in. So a refrigeration cycle is your refrigerator, and if you think of your refrigerator, it's cold in there, and so we're taking the heat out of the system and putting it into the surroundings, and so that would be a refrigeration cycle, and you're trying to cool it down in there by removing the heat essentially, and so the W cycle would be Q out minus Q in. So you can see these are opposite each other. For a power cycle, Q in minus Q out. And this is for refrigeration or heat pump. And then refrigeration cycles, the objective is to cool or refrigerate the space or maintain the temperature of a dwelling or building below that of the surroundings. Refrigeration cycle have a coefficient of performance. So again, we talk about the thermal efficiency of a power cycle. We talk about the coefficient of performance, which is beta, for a refrigeration cycle. And beta equals Q in divided by W of the cycle. And since Q in, or W of the cycle is Q out minus Q in, we get Q in over Q out minus Q in. So this is what beta is. And this is for a refrigeration cycle. Again, the coefficient of performance. Heat pump cycles, the objective is to maintain temperature of a dwelling above that of the surroundings or to provide heat for certain industrial processes that occur at elevated temperature. Heat pump cycle coefficient of performance, similar terminology as a refrigeration cycle. I think that one's name is gamma. Gamma is Q out over W cycle, or Q out over Q out minus Q in. So these come up over and over. It's talking about essentially the coefficient of performance. Well, anyway, we'll see those later as well when we later in this book. But it's important to get them down now. So a process could be. These are different terminology. Really important to know what these things mean because you'll get these clues in a question or in and trying to solve the problem. You need to understand them. So adiabatic means no heat transfer between the system and the surroundings. Isobaric is constant pressure. Isothermal means constant temperature. We also have constant volume, although I don't think it has a fancy name. A reversible are always in equilibrium. A reversible process is always in equilibrium. It happens super, super slow. Again, quasi-equilibrium, we're trying to get a reversible process. Irreversible happens in one direction, and it defines time. So it always goes in a positive time direction. And think about opening a can of soda as the irreversible process. And then polytropic is a quasi-equilibrium process described by these equations, where this one is with volume and this one is with specific volume, where n is also a constant. It's a lot for this chapter, and it's important that you keep working at it. Everything we went over today, and even the rest of the things that we didn't go through in the chapter, will lead towards being able to solve more problems in the future and all the rest of the chapter. So it is important that you dig in and really try to understand all these concepts. Good luck to you. I'll see you in class.